All right, hello, welcome everyone to our second lecture here. So here we are covering the history and evolution of engineering disciplines. So before we get going, let's just briefly review a couple key practice questions from our first class. And so please take a moment if you'd like, and you can pause the video and try these questions on your own, and then we'll discuss. Okay, so our first question, you can see we are asking, as a general rule, you need a minimum of how many hours of study per 1 hour of lecture. So you might remember here, if we refresh our memory, the general rule is for every 1 unit of classes, you need 3 hours per week of time. And if you say that one of those 3 hours is an hour of lecture, that would also correspond to 2 hours study time per 1 hour of lecture. So correct answer for this question is minimum of 2 hours of study per 1 hour of lecture. And remember, it would be 2 hours of study per 1 hour lecture, 3 hours per 1 unit of class. And our second question, this is just a random question for you to start thinking about. Think about what engineering functions sound most interesting to you. And maybe you found that one or more of these functions sound interesting. And that's actually what we're going to talk about today. You'll learn there's a lot more to engineering than just what major you choose. Within your engineering major, you can do any number of these functions. So it's also important to think about what types of work would you like to do as an engineer? Do you want to do design? Do you want to do testing? Do you want to do manufacturing? Or maybe education? Depending on the functions you're interested in, you may want to plan your career and your skill development accordingly. So we'll cover that in more detail during today's class. Okay, so goals for today. So we're going to go ahead and define engineering and also explain how engineers are different from scientists and technologists. We're going to look at a brief history of engineering disciplines. And as noted down here, this is not a history class. History of engineering is fascinating, but we don't have a ton of time to spend on this, so we're going to go through history fairly quickly so we can focus on other topics. So, for the purposes of our class, please pay attention to the key takeaways that are highlighted in these slides and on your handout. And finally, we'll start introducing those job functions within engineering. If you're following along in our textbook, this comes from chapters 1 and 2 of Engineering Your Future. Okay, so definitions of engineering. So there's this organization called ABET. They are the Accreditation Board for Engineering and Technology. They are this organization that goes through and evaluates every engineering degree program, and they put their seal of approval on programs that they think are good. So often you want to attend schools that offer ABET accredited engineering degrees. So ABET defines engineering as the following. Engineering is the profession in which knowledge of the mathematical and natural sciences, gained by study, experience, and practice, is applied with judgment to develop ways to use economically the materials and forces of nature for the benefit of mankind. So that's a mouthful, right? I prefer the short version. So really, at the end of the day, engineers use good judgment. I often call this intuition or spidey sense. Engineers apply knowledge of math and science to develop things. And notice the word apply. We're applying existing knowledge. And finally, we try to benefit people in economical and cost-effective ways. So notice this is maybe a little different than math or science or other sort of STEM areas. Here, we're trying to apply math and science to benefit people and use good judgment. So let's briefly go through then and take a look at a history of engineering. And in terms of history, the thing I like to do is focus on what we can learn from history. So here I've broken down our history of engineering into 10 lessons learned. So let's review the history by looking at 10 important lessons, and please notice the key takeaways are highlighted. So pay attention to those key takeaways. All right, lesson number 1. The earliest engineers did not have engineering degrees. You can read about the prehistoric engineers, and we learned that they designed tools and solved problems using trial and error, and testing, and intuition. There were no engineering degrees. You had to learn by trial and error. A good example is Polynesian boat designers. You may have heard about these Polynesian boat designers, and they were able to sail long distances, and they used math and astronomy to navigate. So, key takeaway here is that early engineers needed to use trial and error, testing, and intuition rather than science. And this is still important today. Besides having an engineering degree, having experience and intuition and being willing to try and learn new things, these are also important. Next lesson. You don't have to reinvent the wheel. Old is not always bad. So here we learn about Mesopotamia. They were an early Middle Eastern city, and many great inventions are credited to Mesopotamia. Mesopotamia developed the wheel, sailing boat, and writing. And as you can see, many of these inventions are still relevant, and they're still in use today. So, key takeaway: wheel, sailing ship, and writing were invented in Mesopotamia. And let's also remember this second point. Engineers don't always have to invent new things. Sometimes a tried and true solution can be very effective and can be good enough to solve your problem. All right, on to lesson 3. Civil engineering is the oldest engineering discipline. We learned that as people settled into cities, all of a sudden people could specialize. Not everybody had to be a farmer anymore. And so we started to develop different kinds of professions, including civil engineers. Civil engineers were needed to build buildings and roads and infrastructure to support early cities. And the earliest civil engineers are credited with building all sorts of great constructions. We have pyramids, Machu Picchu, temples, aqueducts, roads, Great Wall of China. A lot of these really impressive constructions and monuments were built by ancient engineers. And of course, civil engineering was later officially recognized in 1761, and here they were distinguishing civil engineering from military engineering, because civil engineering focused on buildings, transportation, and structural, rather than on building weapons and military type applications. There's a joke that some people say civil engineers build targets and the aerospace engineers build the things that destroy the targets. But either way, civil engineering is an extremely important discipline and considered the oldest engineering discipline. And another great takeaway to remember is that these architectural achievements of early engineers, many of them would still be difficult to make even with today's tools. So it's truly impressive what they were able to accomplish. Okay, moving on. Lesson 4. Early Native Americans were the first sustainability and genetic engineers. Native Americans accomplished a lot. They genetically engineered corn by crossbreeding different grasses and grains. They developed aqueducts and water distribution systems. Incans developed ways to freeze-dry food, and many Native Americans used sustainable agricultural practices. So really, key takeaway here is that we can learn a lot from these early engineers. The Native Americans were excellent agricultural, sustainability, and genetic engineers, and they developed a lot of important methods for food preservation, water distribution, and sustainable agriculture. On to lesson 5. Engineers need to make technology affordable and accessible. So again, affordable meaning, reasonable cost, and accessible meaning widely available. If we revisit our definition of engineering, cost is an important factor. You could engineer the greatest solution in the world, but if it costs too much and it's not available to everyone, then it doesn't really help. So, key thing to think about here is the Industrial Revolution in the 1800s. This is when engineering really took off because machines were developed. And these machines could replace and improve upon manual human labor. But machines needed to be affordable and accessible in order to produce a widespread benefit. And there are examples in history where people developed some very nice machines, but if they were not affordable and accessible, they were unable to make a huge impact. Some good examples include automobile, steam engine, and agriculture and mining equipment. So key takeaway, Industrial Revolution introduced machines and automation. And very important, still relevant today, technology needs to be affordable and accessible in order to benefit consumers. Next lesson, number 6. Mass production requires efficient and safe manufacturing. So, the field of industrial engineering arose when people realized that we need to reduce cost and improve quality when manufacturing large amounts of product. And several engineers pioneered big advances to industrial engineering. You may have heard about Henry Ford's assembly line, which led to a lower cost automobile. And Lillian and Frank Gilbreth were very prevalent pioneers in industrial engineering. And they introduced these time and motion studies to make manufacturing more efficient. So, key takeaway, industrial engineering was born when people needed to make manufacturing safer, faster, and more efficient. If you look at manufacturing today, many of these principles are still in place. All right, lesson 7. One person can't do it all alone. As students, often we complete most of our coursework individually. You have a group project or two, but at the end of the day, you're a one-person team. You'll find when you go into engineering industry that most of the time engineering becomes a team sport. And one person can only do so much before you need to rely on others to help you complete your project. And the good example of this is the history of the computer. Original computers took up entire rooms and were huge, massive pieces of equipment. But the computer really became what it is today, thanks in large part due to collaboration and innovation between teams. There were teams of smart, dedicated people who worked together and allowed the computer to become widespread. An interesting fact about that is Grace Hopper and Bernie Gordon. Grace Hopper helped create computer languages, so her work helped lead to development of programming languages today. And she actually worked very closely with Bernie Gordon, who helped design the first commercial computer. And so rather than compete with each other, they recognized the importance of the technology and they worked together to help advance computing. So, big important point to remember is that innovation and teamwork among multiple people together is really important. And here it's that innovation that allowed computers to become widespread. Number 8, contributions of team members should be acknowledged. This is incredibly important. And one unfortunate fact about engineering is in the past, there are many examples where there's teams where most people or some of the contributors got little to no credit. For example, Thomas Edison is credited with the invention of the light bulb, but you don't really hear much about the team who was working with him. Or the Brooklyn Bridge. Emily Roebling led the project to completion after her husband died and her son fell ill. But you don't necessarily see her name associated with the bridge. And another example, Benjamin Banneker and others helped design Washington, D.C., but the team lead, Andrew Ellicott, got most of the credit. Thankfully, engineering is changing, and in the industry today, a lot of people are a lot more inclusive and aware of the importance of teamwork. Companies have a lot stronger of incentives to have people work together. Because when you recognize and reward entire teams rather than individuals, it can help foster greater collaboration and teamwork among engineers. So, key takeaway, initially, engineering rewarded individuals for achievements. But now the industry is becoming more supportive and inclusive in recognizing entire teams. And I would encourage you, as you work on engineering projects, to keep this in mind. Recognize those who helped you accomplish what your team accomplished. Often it costs very little to thank someone, but it can mean a ton, and recognizing and respecting your team will help you be a better team player and a more successful engineer. All right, 2 more to go. So, lesson number 9. engineering is always evolving with new technology. And you can see from this list that there are many disciplines where engineering has evolved as technology improved. For example, airplane and flight led to aerospace engineering. Automation in farming led to agricultural engineering. We talked about civil engineering, how cities and human settling made civil. Also, when chemists and engineers teamed up to make efficient chemical processes, that led to chemical engineering. Computer and electrical engineering developed with computers and electronics, and similarly, even the industrial and mechanical engineering developed as part of the Industrial Revolution and all the iron and steel. So this is going to continue to happen. As new technology is developed, more engineering disciplines will continue to evolve. So it's important to always keep learning, because as an engineer, you may find that your skill set and knowledge will keep learning and growing to keep up with the latest technology. All right, last history lesson. Engineering is becoming interdisciplinary. When we say interdisciplinary, we mean combining knowledge from many fields. So some of the examples we mentioned, chemical engineering combines chemistry and engineering, or bioengineering involves applying engineering to living systems, or green engineering, combining sustainability and engineering. So you may find that more and more solving new problems often requires interdisciplinary knowledge. You have to combine knowledge from multiple fields in order to solve some of these new and complex problems. So let's do a quick review question. See if you remember. Which of these is the oldest engineering discipline? Pause the video a moment and see if you remember. All right, and if you were thinking civil engineering, you would be correct. Agricultural engineering is not considered to have started until automation and the Industrial Revolution came about, but as we mentioned, civil engineering really became a thing as early as when humans settled into cities. All right, so let's go ahead and move on to what engineers do in the present. And remember, if you do have questions about what's covered so far, feel free to reach out. Okay, so we talked about what is engineering, but it's also important that we distinguish the differences between engineers, scientists, and technologists. Many students come to me and say that they chose to study engineering because they liked math and science, or they liked building stuff. And those are very good reasons to consider engineering. But it's important to know what you're signing up for. So keep in mind the following points. Engineers apply math and science to solve problems, but with a specific application in mind. Most of the time, engineers are not sitting in the lab doing science experiments. They're trying to make a specific product to solve a specific problem at a specific cost. So you're focusing more on applications. Compare that with scientists. Scientists ask why and aim to advance knowledge in a specific area. Scientists are more trying to find knowledge and gain knowledge, publish research. So it's a different goal. So if you're more interested in doing research and diving deep into why something is the way it is, science might be actually a better fit for you. and that's perfectly okay. And finally, to those who like building stuff, it's good to remember technologists. Technologists use existing technology to produce goods. But here's the important point about technologists. Technologists do not create new technology. They do not design new technology. Most of the time, technologists are the ones using their hands to build technology. These are like the workers in the Tesla factory who are assembling the automobiles. They're very skilled at putting together and assembling a finished product. Compare that to the design engineer who might have been designing the actual Tesla automobile, or the scientist who did research to learn about the batteries that power that electric car. So, key takeaway here, please make sure you know the difference between engineers, scientists, and technologists. And make sure you know what you're signing up for if you're pursuing an engineering degree. It's not to say that engineers or scientists or technologists are better than the other. They're all different paths. And so you want to make sure you choose the path that is most interesting and appealing to you. Let's try a practice question. Suppose you are a hiring manager and you want to hire someone who will use existing technology to produce goods. Which person from this list would be the best person for the job? Take a moment and see if you can identify them. So in this case, the correct person to use would be a technologist. Remember, technologists use existing technology to produce goods. So generally, you would want to hire somebody who is qualified for that job. Technologist would be the best choice. All right, so let's go ahead and move on to our last topic for today, which is engineering functions. Many students spend a lot of time thinking about what engineering major they want to choose. But I would encourage you first to think about what engineering function you want to do. It turns out that every engineering major still has jobs that perform the same basic job functions. So, regardless of whether you're a mechanical engineer, an electrical engineer, a computer engineer, all the different engineering majors have people who do research, development, testing, design, analysis, all these different functions. So I would highly encourage you to think about which of these functions interest you the most. These are the functions that you would want to consider learning more about. These functions are common across all disciplines. So let's go ahead and take a closer look at these functions so that you can learn more about each of them. Someday, if you're a hiring manager, you'll want to know which functions are the best ones to hire for that job. So for fun, let's take a slightly different approach. Let's look at some real job postings as examples for each type of function. On the following slides, all of these slides contain an actual job posting I took from searching Indeed.com in the San Francisco Bay Area. So first function is research. So as we said before, engineers are not the same thing as scientists. However, there are engineers who do research. But keep in mind, these research engineers, their focus is not on just finding knowledge. Their focus is on applying some breakthrough technology to solve a problem. So research engineers will design experiments, run simulations. They may have lab technicians who do some of the lab work for you. And they often work for research centers, and very often because there's such a focus on research, you may need a PhD to become a research engineer. But again, the focus is on applying a breakthrough technology. In this example from Memphis Meets, you can see that the focus of this research engineer was developing some prototypes. So, they're evaluating prototypes, they're maintaining lab equipment, they're doing modeling, they're making components, fabricating parts in-house, they're managing partners, they're basically trying to research and develop an early prototype. And so you can see some of the qualifications. They definitely want people who know how to prototype, and in this case, they want people who know about biological stuff. Next is development. Development is a fascinating and challenging area of engineering. In development, you are bridging the gap between the lab research, where you're making prototypes, and the full-scale manufacturing. So development is the one that takes that initial design and brings it to full-scale manufacturing. So development engineers need to know about manufacturing tools, and they work with the design engineers to transition that product to mass production. In development, you often need frequent travel to manufacturing sites, sometimes even internationally. Here's an example from Amazon, a hardware development engineer. And you can see that they're doing a lot of stuff related to manufacturing. They take product from development from concept through development, testing, sustaining. Here, sustaining means sustaining a full manufacturing process. So they're working with other product design teams, support manufacturing test, work with vendors and suppliers, develop test requirements, contribute to design decisions. So lots of focus on bringing an initial design to full manufacturing. And here they are looking for someone with an electrical engineering or hardware expertise. Next is testing. Testing is really important. Test engineers need to verify whether a product works. It's an extremely important part of the engineering process. So test engineers are going to be designing and implementing tests to verify product integrity. They're going to be collecting and reviewing data, and of course, you need a broad set of problem-solving skills and a wide range of tests. In this example, we have a test engineer for TikTok, and you can see that this is actually a software focus, so they're looking for somebody who will track and manage bugs in the software. So they're looking for a computer engineer or electrical engineer, and they're looking for somebody who can manage projects, test tools, implement and design testing. So very important for identifying issues and solving them. Next engineering function is design. Design engineers are sort of the classic engineer. So if you think of the classic engineer who's designing something and then putting that design into a product, that is a design engineer. What a design engineer does is they are responsible for designing part of a product. And so their job is to generate what's called a product specification. The specification will explain all the details of that design. And in order to make sure that the design works, design engineers will build prototypes run simulations, maybe even perform some basic testing to make sure the design works. The design engineer also has to work with development and manufacturing in order to mass produce the design. So they need to help with the transition. And as a design engineer, cost and time to market are often very important factors in your design. The marketing teams and the customers will be potentially contacting you quite a bit, asking when your design will be ready. And so you want to make sure that you also create your design within the project timeline and within the cost targets, which is much easier said than done in some cases. Example of design engineer is this iPhone hardware system design engineer with Apple. And notice they want somebody to be at the center of their product development, impact on design, and they want people who know about electrical engineering fundamentals, system architecture. They want people who know how to do, different types of prototyping and different types of design in hardware. Next engineering function is analysis. If you're one of those people who like to crunch numbers, run simulations, or make models, then analysis might be the function for you. It turns out that it's very expensive and time-consuming to make prototypes. Sometimes we don't have enough time to build and test a prototype before making a design decision. So analysis engineers are really important. Analysis engineers use models and computer tools to help simulate products. And often they will run different kinds of tests to validate these models. Analysis engineers help design engineers make decisions. If we want to implement some new part for a design, we may need to run simulations to see how that design might work. And so analysis engineers are key to help analyze data and run simulations to verify that our design will work as expected. Another example from Apple, you see this one is working on a performance model development. And so they notice they're working with design teams. They're making models and they're analyzing results, providing feedback to the design team, correlating performance model against the specifications. So a lot of focus on making models, reviewing data, and guiding design decisions. Next function is systems. So systems engineers are really interesting because they put all the pieces together. So you remember that design engineers make a single piece. So design engineers typically make one part. Systems engineers combine all the parts together. So systems engineers need to work with all the design engineers to combine the pieces together and form the final product. Also, they need to make sure that that final product meets the design requirements. Got to make sure that the final product will satisfy the customer. Systems engineers are also responsible for defining what the design requirements are. So they may work with customers, marketing, and others to figure out what requirements need to go into that product. Example from Facebook, hardware systems engineer. And Notice they're working with vendors and teams to figure out what is needed in their hardware products. And notice there's lots of discussions, there's lots of data analysis, troubleshooting. So systems engineers focus on the big picture and putting all the pieces together. Notice they often need more work experience too, because they want somebody who knows engineering really well and who can help combine the smaller parts into the big product. Next one, manufacturing and construction. Manufacturing and construction is a very challenging part of engineering, and you might think, oh, that's easy, they just have to put the design together. How hard could that be? It turns out developing processes which are repeatable and produce a product on time and within the cost target, that can be incredibly challenging. And so manufacturing engineers work with diverse teams, and they can go to different countries to do travel, to meet with suppliers and factory partners. And they also work closely with development engineers in order to make the product mass produced. So one example from Waymo, you see that they are developing and approving process flows or manufacturing plans for new products. They're doing design reviews, they're designing actual fixtures used in the process, managing manufacturing partners, providing design feedback. So lots of focus on actually building the final product. Next function, operations and maintenance. So once all the design is finished and everything is kind of deployed to the customer, that's when operations and maintenance comes in. They maintain the ongoing performance. So they maintain ongoing performance of a given product. So maybe the product has been released for a while, and now it's just up to the operations and maintenance team to make sure everything continues working as expected. So they oversee that ongoing performance, and they make sure the product continues to work after it has been released into the real world. So these engineers have a lot of expertise, and they work with a lot of different people to make sure everything keeps working. In this Facebook example, you can see that they're basically working to make sure that everything keeps running. So, they're trying to contribute to projects, they're making sure that they're looking at business impact, they're building systems, highly reliable systems, and they're making sure that the final product keeps running. Next, we have technical support. Technical support is a very important function because it is the link between the customer and the product. What happens if you sell the product to a customer and the customer has a question or runs into a problem? That's when you call the technical support engineer. Technical support engineers often will visit the customers and oversee product setup. They'll also help customers troubleshoot problems. And technical support engineers typically don't know everything about the product, but they know how to find the answer. So maybe they'll contact a more experienced design engineer on the team to figure out how to solve the problem. Technical support engineers must have really good people skills and problem-solving skills. You can see in this job description, they're providing direct support to customers. They're collecting data, change recommendations, recommending corrective actions, real-time phone or remote sessions. So they're supporting the customer and also providing feedback back to the rest of the engineers. Next one, customer support. This is a little different than technical support. Technical support is more focused on problems and immediate customer support. So technical is more focused on problems. The customer support, this is more focused on relationships. Especially if you have a big customer who's buying millions of dollars of your product, you want to make sure that that customer is satisfied and that they keep coming back to buy more product from you. So the customer support engineer is very focused on the business aspect of the customer relationship. They're often involved with things like warranties and contracts, trade-ins. So these people have both product and business expertise. So customer support engineers, they want to make sure the long-term relationship with customers is maintained. And you can see in this example from Intel, you can see they're providing training, demos, assistance. They're making training courses, feedback. They're basically working very closely with customers to help them with the products and keep them satisfied. Next, we have sales engineers. So if you are a people person and you're good at selling stuff, sales engineers might be a good function for you. Sales engineers need to have good interpersonal skills to sell products. But many times, the people buying your products will also be engineers. So you need to be able to answer tricky technical questions. So sales engineers must be able to answer technical questions about the product and help customers find the right product for them. Often these engineers travel a lot to visit customers and to go to industry conferences. And you can see in this example, the sales engineer is very much involved with both the customer and the business side of engineering. They make business plans, they manage their assigned customers, they try to develop and establish relationships with customers, drive new business demand, provide timely and accurate revenue forecasts, pricing negotiations. So again, very, very much a sales background as well as an engineering background. Next, we have consulting. Consulting engineers can be very interesting because they can either be self-employed or they may work for a firm. And often, consulting engineers are not actually making products directly to customers. Instead, they are selling their knowledge and technical expertise to help other engineers solve their problems. So often other companies will hire consulting engineers on a contract to help with a specific project. And depending on the nature of the client and the assignment, you might need to be a registered professional engineer and you may need to travel. And basically, as a consulting engineer, you often need to have a lot of existing experience because they're looking for somebody who can quickly make an impact to solve a given problem. Just a couple functions left. This one is management. Now, when you hear management, the first thing you might think of is managing a team. And managing people is definitely an important function in engineering. But you could also be managing products, suppliers, components, people. So management is not necessarily just people management. It could also be some other part of the finished product. And typically in a management type role, you need a little bit more experience and leadership skills because you need to have enough knowledge of working with people and working with products in order to be able to make an impact. The example here is a people manager, so they're hiring and retaining staff. They're kind of maintaining the engineering development cycle, managing deliverables. So here, the manager is focused on guiding their team. The team does most of the engineering work, while the manager oversees, removes roadblocks, and makes sure the team is moving in the right direction. All right, that's about it for functions. Just a couple more of interest here. Even outside of engineering, engineers can be involved with patents or intellectual property. So these engineers are using their expertise to help others protect their ideas. There's also education, like professors or school teachers, and even in medicine or Wall Street. So the key takeaway here is that an engineer's problem-solving skills are really useful in many different professions. Let's do a couple quick review questions. Suppose you're considering an engineering career path, but you don't want to travel a lot. Which of these functions would likely require the least amount of business travel? Which one do you think? Pause the video a moment if you want to think about it. All right, the correct answer here is choice D, analysis. Sales engineers need to visit customers. Development and manufacturing may need to travel to factories or visit suppliers and other people. But analysis engineers, they're primarily working on making models, simulations. So it's something to think about. Depending on how much business travel you'd be comfortable doing, you want to make sure that the engineering functions you choose will support the work-life balance you want. Let's do one more question. Suppose you're a manager at a company and you have finished your research and prototyping. You're now setting up a manufacturing line. You need to build large amounts of your product. Which team of engineers would you hire to be most successful? Go ahead and pause the video a moment. Think about which team you would choose. So, what do you think? We know that we already finished research and prototyping, so probably would not be choice B. Also, we're not ready to sell yet, so probably not choice C. And consulting wouldn't necessarily help us with a ton of product. In this case, choice A would be the best choice. Remember, development engineers are the ones that transition our product to manufacturing. So we definitely want development and test, management to oversee the various parts, and even operations to keep the manufacturing going. So choice A would be the best option. Finally, as we finish up today's class, I'd like to leave you with this question. What functions interest you the most? Many students focus primarily on deciding an engineering major. And while it's certainly good to think about majors, and we'll talk about majors in the next video, also consider what functions would be the best fit for you. And these are some good questions to ask. Do you want to be a people manager? Do you want to do research? Do you prefer to work alone or with a team? Do you want to build things or crunch data? Do you want to sit in an office, work in a lab, or even work from home? How introverted or extroverted are you? Do you like working with customers? Do you want a fast-paced environment or a slow pace? Do you want to work independently? How much work-life balance do you want? Do you want to do a lot of business travel or work from home? How much ambiguity and uncertainty do you like? Do you like powering through the unknown or following a set path? Maybe you know the answers to these questions, and maybe you're not sure. But keep them in mind, and hopefully over time, it will help guide you towards a career that's a good fit for you. And finally, some advice to those who are unsure. Remember, it's okay to have not everything figured out just yet. My biggest advice is to try different things and see what you like best. If you're not sure, keep as many doors open as possible. You could always choose to study something a little bit broader and then zoom in on something as you learn more about what you like. Engineering opens doors, so even if you have an engineering degree, it creates many opportunities to try different things. And finally, remember it's okay to change functions. I myself have worked in research, design, development, management, and education. So just because you start out in one function doesn't mean you can't go somewhere else later. All right, so I hope you found this review of engineering helpful, and please make sure you remember the key points. Make sure you recognize those different job functions and think about what job functions are most interesting to you. If you're really curious, try searching Indeed.com for jobs that interest you. Think about what skills and education are needed. You may find that you'll do this as part of our homework. In our next video, we'll take a closer look at engineering majors. Feel free to reach out if you have any questions, and we'll see you in the next video.